Okay, we're back. We're going to talk about the size of an atom because that is one of the periodic properties. Okay, as you can imagine, when you go down a column, atoms get bigger. Okay, one of the things that you're going to have to do on the AP test is you're going to have to explain the reasons behind why these trends occur. So like your first year of chemistry, you just learned the trends probably, right? Atomic size increases down, decreases across. And that's a good place to start. But this year you're going to have to be able to explain why, okay? So on this slide, for example, all right, they're explaining to you how they actually measure the radius of an atom. Because obviously a radius is really, really small, okay? And so if they're measuring this, how are they measuring an atom? Well, what they do is they take two atoms that are bonded together and they measure the distance from the center, from the center of one atom to the center of the other, okay? So the center of the nucleus to the center of the other nucleus. And then what they do is they divide that in half, and that gives you the radius of one atom. And so if you use the diatomic molecules, so like nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen, like if you start there and then you understand the size of those atoms, you can then measure the bond lengths between them and other atoms and figure out how much was by hydrogen, for example, versus what amount comes from carbon. So that's how they do it, okay? Now, so what happens, okay? Well, as we said, as you can imagine, atomic radius increases going down a column. This should make sense to you because you know with each successive element in a group, you are adding energy levels. So for example, the alkali metals, lithium ends in 2s1. That's the second energy level. Sodium ends in 3s1. That's the third. Potassium 4s1. Rubidium 5s1. So you're adding more circles around the nucleus, if you will, and you're getting wider and wider and wider as you go. Okay, so that makes sense. Left to right across the periodic table, atomic size decreases, and sometimes people have a hard time understanding why. But you have to go back to the concept of nuclear charge. Remember, we talked about sodium and magnesium being next to each other, right? And we said that sodium has a nuclear charge of +1 and magnesium has a nuclear charge of +2. They both have 10 core electrons, okay? So what that means is that magnesium has more positive protons, well, all protons are positive, but it has more protons, which are positive, in its nucleus, okay? And it's also, its widest level is the 3s sublevel, just like sodium's. So sodium and magnesium, because they're in the same row, are equally wide in terms of their sublevels. So then the question is, well, then how do they compare to each other radius-wise? And as you go across the sublevel from left to right, the radii decrease because if that outer level is at the same point, like if you weren't accounting for electrons, but magnesium has more protons than sodium does in its nucleus, that means that nucleus is able to pull that outer energy level in just a little bit tighter and make that more attracted to the nucleus because there are more protons. So again, same thing, you'll notice, pick any one of these main group elements. If you go across like 3p, for example, aluminum is a little bit bigger than silicon, which is a little bit bigger than phosphorus. Okay, we'll talk about why there's this little blip here. But then sulfur, chlorine, argon, you know, they're very similar because, again, you're talking about how many protons are in the nucleus, but you're comparing the 3p level for all of these, okay? So that's how that works. So again, remember, you have to explain the trend and the reason behind the trend. Okay, let's move on to ions. How are ions different than atoms? Well, you have to keep in mind, cations lose electrons and anions gain electrons, okay? So for example, I'm going to stick with sodium. Sodium loses an electron to become a sodium ion. Well, if that electron that it loses is in 3s1, now it ends at 2p6. It lost an entire energy level, right? It doesn't need the 3s anymore because it got rid of that electron. So of course a cation is going to be smaller than its parent ion. That's what you would call that. Let's look at an anion though, okay? Let's look at chlorine. What's chlorine going to do? Chlorine wants to gain an electron, okay? Well, so again, we're looking at 3p5 versus 3p6. So same level, we haven't gotten rid of any levels, but what have we done? We've added electrons to this outer level, which means now there's more repulsion than there was before, okay? So when you're considering the size of an ion, you have to think about the nuclear charge, because that does still have an impact, like magnesium is still going to be smaller than sodium, whether it's the atom or the ion, because in either case, there's still 12 electrons and protons in this nucleus, where here there's only 11. You have to consider the number of electrons. When you're adding electrons, which we do with anions, that means you're creating more repulsion, which means they're going to want to get a little further away from each other and spread out. And then you have to consider which orbitals or sublevels we're talking. Because again, alkali metals, alkaline earth metals, they're getting rid of their outer electrons, which are in the outer sublevels, which means they're actually decreasing in size. Okay? So, hold on one second.